Hello everyone, my name is Daniel Ibarra. I'm an architect and an environmental design consultant. The paper I'm presenting reports on an environmental design analysis that was carried out during the early design stages of a holiday housing development, aiming to detect the energy viability of the project located in Baja California Sur, Mexico. The analysis is based on the premise that there are no services available on site, no electricity, potable water, or gas. The success of the project relies on the possibility to produce and store its own energy without compromising the thermal comfort of the interior spaces. La Paz weather station was used for the analysis. After studying the hot and dry climate of the site, different passive design strategies were tested to improve thermal comfort. The annual climate was divided into three main categories according to the dry bulb temperature: mild from December to March, warm April and November, and the hot season from May to October. The development consists of a 704,000 square meter site with 6 three-story buildings, each floor with an apartment of 130 square meters plus terrace. The study focused its analysis on the building that is expected to be the most exposed one. As previously described, the effectiveness of the passive design and material optimization strategies were tested on the chosen building for the base case. In general, the building is divided into 3 levels. For the study, each level represented a general unit composed by various thermal zones. To establish the base case, the model included the typical materials used in the area: hollow concrete blocks, single glazed windows, concrete slabs with clay tiles and plaster coatings on soffits and walls. Insulation was considered for the roof. At first, the analysis considered an enclosed scenario with no natural ventilation to calculate the cooling loads. This chart shows how the cooling peaks during the warm and hot season. Afterwards, daytime natural ventilation was implemented in order to establish a baseline to improve the building performance with passive strategies. The natural ventilation strategy was the result of the initial climate analysis, in which, after classifying the annual phases for the outdoor temperature, it was established that during the period classified as mild, natural ventilation was enabled during day, and during the warm and hot season, only night ventilation was implemented during daytime due to the high temperatures. After optimizing natural ventilation schedule, comfort on a typical hot day was increased for the master bedroom by 32% and for the living room, 43%. Shading on the proposal was addressed in 2 manners: the geometry of the building and the additional elements of solar control. First, the building geometry, staggering of the building geometry, each level shades the one below. As for the openings on the facade, all windows were placed inwards between 50 and 75 centimeters. And secondly, solar control elements, such as louvers on the terrace, were placed since the base case, but after the solar radiation analysis, additional shading devices were included on the windows and on the terrace to protect from the western solar exposure during the evening. Although the effects of optimized solar control were barely notable on the comfort hours, shading had an impact, delaying and reducing the indoor operative temperature peak by 1 K. For the construction set optimization, insulation was applied on the exposed surfaces. Thermal mass was increased by thickening the concrete slab and using terracotta bricks. The result that these improvements had after the simulations were notable, increasing comfort by almost 10% on a hot day. Despite this comfort percentage still accounts for around a third of the time for the level 1 and 2, almost a fifth on the ground floor, the maximum interior operative temperature rarely exceeded 34 degrees. So active strategies such as air movement using low energy consumption ceiling fans and evaporative cooling on the outdoor terrace using water nebulizers were implemented. So physiological cooling can be achieved after air movement by several degrees, depending on the air velocity. So after increasing the air velocity between 0.5 and up to 2 meters per second, thermal comfort was achieved for almost all the time. Finally, taking advantage of the low humidity percentage during daytime, evaporative cooling could be implemented successfully for the terraces adjacent to the living room and the main bedroom. If air humidity percentage is increased by 20%, drivable temperature could drop by 35 to 28 degrees. After testing the previous strategies on the annual comfort hours, the result showed that overheating was dramatically reduced or avoided completely for all the floors. After the strategies tested before provided enough evidence to suggest that the viability of the project does not depend on the installation of mechanical cooling, the energy consumption was calculated for the two final scenarios, with and without mechanical cooling, managing to reduce by up to 79% the electric energy consumption. In conclusion, the analysis yields enough evidence to suggest that if the strategies were implemented as described, energy savings of up to 79% could be achieved in respect to the base case. The thermal simulation gives enough evidence to suggest that the use of air cooling equipment could be avoided and still achieve comfortable spaces. If so, that would represent significant savings of up to 89% in terms of the initial investment of the energy generation system, supporting the energy viability of the project by acquiring solar panels and energy storage batteries. Finally, I would like to conclude by thanking the confidence given to me by the design team at Dos Jaimes Arquitectos, especially the project leader, the architect Jaime Guzmán Corcuera, for choosing me as their environmental design consultant.